Today, we're going to deeply understand one of the most important integrals in calculus, the integral of 1 over x squared. What does this equal, and more importantly, why? Let's find out step by step. Now, some students immediately apply the power rule and get negative 1 over x. And they're actually right. But do they really understand why? Before we dive into the algebra, let's actually visualize what we're integrating. This is the key to deep understanding. Here's the graph of y equals 1 over x squared. Notice how it shoots up to infinity as x approaches 0, and gradually approaches 0 as x gets larger. Notice something important. This function is always positive. No matter if x is positive or negative, x squared is always positive, so 1 over x squared is always positive. Now, what does integrating this function actually mean? The integral represents the area under the curve. For example, the definite integral from 1 to 3 represents this shaded area. The indefinite integral, which is what we're finding, gives us a function that can calculate the area for any bounds we choose. The fundamental idea of integration is approximating the area with rectangles. Start with a few rectangles. The approximation is rough, but it gives us an idea. Add more rectangles, the approximation gets better. Even more rectangles, and in the limit, as we use infinitely many infinitely thin rectangles, we get the exact area. This is the magic of calculus. Now, instead of computing infinite sums, we have a powerful shortcut, the power rule for integration. The power rule states, the integral of x to the n equals x to the n plus 1 divided by n plus 1 plus a constant c. This works for any n except negative 1. The recipe is simple. Add 1 to the exponent, then divide by that new exponent. Let's see why this works by checking the derivative. But why does this rule work? Let's verify it. Remember, if f of x is an antiderivative of f of x, then the derivative of f equals f. Let's check. If f of x equals x to the n plus 1 over n plus 1, taking the derivative using the power rule for derivatives, we bring down the exponent n plus 1 and reduce the power by 1. The n plus 1 cancels, and we get x to the n. That's exactly our original function, so the power rule is verified. Now let's apply this to our integral, the integral of 1 over x squared. Step 1. We need to rewrite this in the form x to the n. Remember, 1 over x squared is the same as x to the negative 2. This is the key insight. The negative exponent lets us use the power rule. Step 2. Our n value is negative 2. Step 3. We apply the power rule. Add 1 to the exponent. Negative 2 plus 1 is negative 1. Divide by negative 1. Step 4. Simplify. Negative 2 plus 1 is negative 1. Dividing by negative 1 just flips the sign. And x to the negative 1 is the same as 1 over x. So our answer is negative 1 over x plus c. And there we have it. The integral of 1 over x squared equals negative 1 over x plus a constant c. But how do we know this is correct? We verify by taking the derivative. If we differentiate our answer, we should get back the original function. Let's take the derivative of negative 1 over x plus c, rewriting as negative x to the negative 1 plus the derivative of a constant, which is 0. Using the power rule for derivatives, bring down the exponent negative 1 and reduce the power by 1. The negatives cancel, and we get x to the negative 2, which is 1 over x squared. That's exactly our original function. Our answer is verified. Now let's use our result to solve an actual problem. Let's find the area under 1 over x squared from x equals 1 to x equals 2. We evaluate our antiderivative at the bounds. Plugging in 2 and 1, negative 1/2 plus 1 equals 1/2. So the exact area under the curve from 1 to 2 is exactly 1/2. Now, there's something crucial we must address. Our answer has a restriction. Our answer, negative 1 over x plus c, is undefined when x equals 0. You cannot divide by 0. So our antiderivative is valid on two separate intervals, from negative infinity to 0, or from 0 to positive infinity. The key point is we cannot integrate across x equals 0. Here's a question many students secretly ask. Why isn't the answer natural log of x? Some students confuse this with the integral of 1 over x, which does equal natural log of x. The integral of 1 over x equals natural log of the absolute value of x, but the integral of 1 over x squared equals negative 1 over x. These are completely different. The exponent makes all the difference. 1 over x is x to the negative 1. 1 over x squared is x to the negative 2. The power rule applies to negative 2, giving us negative 1 over x. But negative 1 is special. It gives us the logarithm. Let's gain some geometric intuition. How fast does 1 over x squared actually decrease? Look at the graph of 1 over x squared. At x equals 1, the height is 1. At x equals 2, the height is 1/4. At x equals 4, the height is 1/16. Notice the pattern. When x doubles, the height doesn't just halve, it quarters. This rapid decay is why the total area under the curve stays finite, even though the curve extends to infinity. Here's a profound insight that separates calculus students from calculus masters. Let's compare two similar-looking functions, 1 over x and 1 over x squared. Both approach 0 as x gets large. Both blow up near 0. But here's the shocking truth. The integral of 1 over x from 1 to infinity is infinite. The area never stops accumulating. But the integral of 1 over x squared from 1 to infinity equals exactly 1, a finite number. The difference is the rate of decay. 1 over x squared decays fast enough that the total area converges to a finite value. 1 over x decays too slowly. The area keeps growing forever. This is called the p-test in calculus, and it's one of the most important convergence results. Let's recap the key takeaways. First, rewrite fractions using negative exponents. Second, apply the power rule. Add 1 to the exponent and divide by the new exponent. Third, always verify your answer by taking the derivative. Fourth, remember the answer is only valid where x is not 0. Fifth, 1 over x squared decays fast enough for the area to converge. And sixth, 1 over x decays too slowly, so its integral diverges to infinity. Thanks for watching. If you found this helpful, make sure to like and subscribe for more deep dives into mathematics.